Hello, Chem 2. Welcome back to the second part of our reactions and rate and concentration video, section 11-2 of chapter 11. Let's get started. So here's a second example. We got a couple more to do today, one of which is really complicated. Here's another example. We have 2NO plus O2 to give you 2NO2. And here's the numbers. Now notice these numbers are a little more complicated. Okay, they're not as clean and crisp as the other one. It would be nice if we were to take the time and energy to make sure all of our numbers were really clean, but this one we didn't, but we can still do this. So same logic is going to take place, We're going to go ahead and look at what happens to concentrations as other concentrations stay the same. So for nitrogen monoxide, between trial 1 and trial 2, the nitrogen monoxide increases by a factor of 2. But if you notice that, the oxygen does not stay the same. So we want to use trial 1 and trial 3. So trial 1 and trial 3, nitrogen monoxide doubles while the oxygen stays the same. And then we look at our rate. What happens to the rate? Well, the rate quadrupled. That means the rate law with respect to nitrogen monoxide is going to be second order. Then you do the same thing. Let's find a trial where oxygen doubles while nitrogen monoxide stays the same. Did you find it? That's right. Between trial 3 and trial 2, oxygen doubles while nitrogen monoxide stays the same. So we can use these two. So then we go over here and we say, well, what happens to the concentration? What happens to the rate? Well, this looks weird, but notice over here, the exponents are different. This is 10 to the negative second. This is 10 to the negative first. So if I had both of them at the 10 negative second, this would be 11.3. Well, that shows me that I'm really close to doubling. So I have a doubling of the concentration. As I double the concentration of oxygen while keeping nitrogen monoxide constant, the rate of the reaction is going to double. So what that means is it is first order with respect to oxygen. And then last but not least, the last thing you do is you go ahead and you figure out what the rate law constant is. What is K? And what we have to do for that is we need to just pick a trial. So for trial 1, if I do the math, this is what I get. For trial 2, I pick a trial, I get this. Trial 3, I get this. And notice 1 and 3 are identical, and 2 is a little bit different. This is going to be the first time, I think, in this class where you're going to have to be okay with pretty darn close. We saw it when we were doing empirical formulas where, scientific significant figures and such make your numbers off a little bit. This is also one of those places. Because this rate is doubling of this, but the numbers are not exactly double, you're going to have a slight alteration, but they're pretty close. If I had the rate law as 1 and 1, these numbers would be way off. So it depends, and this is one of the things about showing work, it depends on which rate law, which trial you use as to what answer you're going to get in some cases. Okay, let's try another one. You go ahead and try this one. Go ahead and pause the video. Try this one. The numbers are a little cleaner, and then I'll come back and see how you did. Hit the pause. I'll be back. So how'd it go? Did you get that it was second order with respect to nitrogen monoxide and first order with respect to chlorine? And then the rate law constant actually should have been 9.12 molarities per hour. So it should have been molarities to the second negative 2 and hours to the negative 1. Did you get that? Good. Now this is the last example, and this is the last we're going to do. And I said there's just going to be one that's really tough, and this is it. Because we have a problem, and you might notice the problem right off the bat. what we always want to look for is situations where a concentration changes while all the other concentrations stay the same. And trial A never stays the same. What are we going to do? Well, there's two different approaches here. One's mathematical, and one is where you have to conceptually understand what's going on and do a little creative math. And I'm going to show you both examples, and we'll see how this goes. So the first thing we do is we take care of the part we do know. First thing we do is we say, well, we know that in respect to A, as A triples, while B stays the same, the rate is going to increase by a factor of 9. 3 to what power is 9? That's going to be 2. So we know that the rate law with respect to A is going to be second order. That we know. That's easy. The trouble is figuring out what the rate law is with respect to B. Because if you look at this, I can choose B increasing from 1 to 2.5, but A doesn't stay the same, or going from 1 to 2.5, but A doesn't stay the same. I have no way to keep A the same because A is never the same. So there's two ways to approach this. Okay, we can either use algebra or we can create a fourth trial. Both of which have their merits, both of which have their strengths. If you're very strong in algebra and are able to manipulate your variables, then that's your answer. If you very clearly understand so far with this whole 2 PowerPoints, how these rates will change while you change concentrations, maybe the creation of fourth trial is the same. Now, creation of fourth trial doesn't mean we're going to actually run a fourth trial. It means we're going to mathematically determine what would happen at a fourth trial. So let me show you the algebra first. Okay, so suppose we want to use algebra. So if we choose to use algebra, here's what we need to do. We need to pick 2 trials where B changes. So we could not pick trial 1 and trial 2. We can pick either trial 1 and trial 3 or 2 and trial 3. But we have to pick 2 trials where B changes. Make sure B changes. If B doesn't change, if you choose 2 trials randomly without thinking at all, and you pick 2 where B changes, you cannot determine what the rate law is using the algebra method. So pick 2. I'm going to pick 1 and 3. Why? Because I did. I don't know. I just picked 1 and 3. So what I need to do is I need to plug the concentration of A, concentration of B, and rate into this expression twice. So I'm going to go ahead and take my expression and say for trial 1, it's 2 times K times 1 to the second, 1 to the Y. I don't know what Y is. And I'm going to do it for trial, this actually should say trial 3. For trial 3, 31.3, K, 2.25 to the second, 2.50 to the Y. Okay, so what I have is 2 equations and 2 unknowns. So if you go back to algebra, you know that when you have 2 equations with 2 unknowns, then you can use systems of equations to solve for both the Y and the K. So you can use algebra at this point to figure out what Y and K are, because you know K is the same for both reactions or both equations, and Y is the same for both equations. So we're going to solve for K and Y. Let's first solve for Y. What I find to be the best way to do this, and it's kind of a cheater method, but I'll literally take in the numerator of a series of ratios, I will put one trial, and then in the denominator, I will put the other one. So notice I picked the big one. I picked 31 as being my rate. I put that in the top. I like using numbers that are greater than 1. That's all. You could have done it the other way around. You just would have had a small fraction rather than a fraction greater than 1. So 31.3 times K, 2.5 to the second, 2.5 to the Y, all that over 2 and K, blah, blah, blah. Okay, so I have that. And then I'm going to realize, wait a second, when I do this, K over K, they're going to cancel. So I'm going to get rid of my K's. And I'm left with 31.3 divided by 2. That's 15.95. 2.5 to the second divided by 1.0 to the second. Well, that's 2.5 to the second. And then I'm going to go ahead and not distribute. I'm gonna set aside and say 2.5 to the y divided by 1 to the y is the same as 2.5 over 1 to the y. And I'm going to solve for y. So I do the math. I divide both sides by 6.25. And then I find that 15.65 divided by 6.25 is 2.5. 2.5 divided by 1 is 2.5. 2.5 to the y is 2.5. Well, what's y? Well, that's simple. Y is 1. So my rate law is rate equals k, a to the second, b to the first. And I've determined that my rate order with respect to b is going to be a 1. That's using algebra. Literally, the idea of using algebra is to simply pick two trials where b is going to change. It doesn't matter which two trials you choose, and put all the data into the rate law expression as you know it. And then you go back and you solve for k, the same way we did before. So how would we do this with the fourth trial method? Well, that's a little trickier and it requires a little better explanation. So let's look at the fourth trial method. So what we want to do, if we're going to do the fourth trial method, is we need to create a fourth trial. Duh. Okay, now here's the part. We know what happens when we change A. We do not know what happens when we change B. So when we're creating a fourth trial, we have to use one of the other trials and change A, but not change B. So what I'm going to do is I'm going to change, and I'm going to make the 1 multiply it times 2.5. Why 2.5? Because then it'll match in trial number 3. So if I increase f, I factor 2.5 while keeping b the same. I know that if I increase the a by a factor of 2.5 while keeping b the same, what's that going to do to the rate? Well, since A is second order, it's going to increase the rate by a factor of 2.5 to the second, or 6.25. And 2 times 6.25 is 12.5. I now have a fourth trial. And I know that would be what would happen because I did not change B. I only changed A. But now what do I have? I now have two trials where B changes and A stays the same. And I can see what happens to the rate. That also increases by a factor of 2.5. And since B increased by a factor of 2.5 and rate increased by a factor of 2.5, just like our last example, then our rate turns out to be first order with respect to rate. Okay, so there's two different ways to get the exact same answer. They both require a bit of work. They both require a bit of logic, but they both do work. So, in the classroom situation, I would provide this data and allow you to try this on your own. You can go ahead and do that. I'm going to leave this here. Maybe I'll use that for Thursday's example. In class, in the flex hour, I'll use this example as the how would you do it, and we'll talk about how that goes about. So what's next? Well, that's all we're going to do for this week. I might put together one more video or grab some more stuff off YouTube and put it onto OneNote, but that's all I want to do for this week. I want to go ahead and talk about yesterday's, what is reaction rates, and then give you a chance to practice interpreting these initial rate data. The next thing we're going to do, which will be the early part of next week, is we will start analyzing data that shows how the concentration changes over time. So, as is always the case, be safe, be healthy, practice that social distancing, and now get that mask so if you do go out in public, you actually cover your face so that we're not going to spread this crazy virus any more than it does by the natural occurrences that are going on out there. Let's flatten that curve. Maybe, just maybe, I'll get to see you later on this year. You guys have a great day. Always remember, never forget, sig figs really do matter. You have a great day. I'll see you on Tuesday or Thursday in Flex Chat to discuss these concepts a little more. Toodles.